begin. Okay, I'm gonna start. Button. Okay, where did I leave off last time? So I was doing best time to buy and sell stock. I think I completed that. Look at my notes. I guess I can look at it here too. Let's see. There was a sliding window. So I'm not gonna do sliding window. I'm gonna continue with binary search. I did this question last time and it beat me up. So I think I'm gonna move on to the next one. Also, I wonder what people thought about that question because I have a feeling other people struggle with it. Brick by brick, we'll all be at them. I think someone helped me with this one. But I'm going to move on to, let's see, search a 2D matrix. I'm going to put that on my notes. Search a 2D matrix. Okay, so what is the question? Look at the question first. I wonder if this is like the Sudoku question. Okay, so you're giving a 2D array and a target. Each row in the matrix is sorted in non-decreasing order. Okay. First integer of every row is greater than the last integer of the previous row. Okay, the example is 1 for row 1, then it's 10 and 14. So it's also increasing as we go down in rows. For every column, just like for every column, it says return true if target exists within matrix or false otherwise. Okay, I'm not going to worry about the time complexity. I think I could just solve the question that they're asking. Okay, I'm going to take the example image onto a whiteboard. Let's see. Okay, what was the target? 10? What's a good way to search this? Well, it's binary search, right? So from the first question on binary search, we learned that we can prune certain sides of the array if the middle point was not in our target. So I guess we can take the same approach with this one. It's just 2D now, so I think this one just means like we can remove anything from any column and row. I think that's what it's trying to say. Whereas before it was just a single array, and we can just, you know, remove anything on the left side or the right side. This one's 2D. What I'm thinking is there's going to be a way to remove like a row and multiple columns, something like this. Look for our target, given some condition. Our target is supposed to be 10, the example. Okay, how can we, we could just traverse every array, like every row, right? Treat every row as its own array, traverse it column by column. If it's not there, we just move to the next row. I feel like that's a very trivial solution. I'm assuming that's part of the first hint. And he also says they're in increasing order, so we can kind of traverse them by, I'm trying to think, let's see, by rows instead of by columns. We can traverse them by rows. And then that's how we would know if we should trim the bottom rows or the top rows. So this is what I'm thinking. For example, let's say we start at so there would be 10 rows, something like this. Rows and columns, to n. Looks like it's not squared. What we can do is we can go to the n/2 row and then look at the first value in that row. This one's coincidentally the answer, so it doesn't really count. Let's grab the other. Oh, I guess we could just move the target. What does he move the target to in the example? 15. Okay, we could try 15 or 14. Actually, we could do 14 because that one does exist. So with the target being 14, we'll start at where the circle's at. And then we can do, let's see, we can check that first value. Do we have to check the first and last value of the same row? Looks like we do. This specific row increments 1 by 1, but the previous row we skipped 3, and then all the values between 4 and 8. So that's a good way to do this. I feel like we would have to validate the number at the beginning of the row and at the end of the row before we can eliminate any rows. Because, okay, we can't even make the assumption that the number will exist in the same row. For example, for this one, we would start at 10, which is less than our target. Which means we don't have to check any of the previous rows, which is good. But before we can say it does not exist on the rows after the current one, we would have to check the last value. So we could say something like this, like instead of being 13, let's say this one was 15. 14 wouldn't exist here. It couldn't exist there, I think. It would have to be like, it'd be like 16 or something. Yeah, 14 couldn't exist in the next row because all the values, as we go down the rows, all the values are also greater than the values in the previous row. So we couldn't have 14 there. So this would have to be something like 16 or something. 16, no greater than 20. I think they could also be, are they unique? I think it mentions that. Just says they're non-decreasing. Okay, and the rows and columns are not equal. Or they could be equal, actually. Okay, regardless, if we check the last value in our row, we could definitively say if the next rows should be even checked, should be checked. So for example, if we checked 10 already, we know that target is greater than 10, and before we could eliminate the next row, we could check the last value in the current row and say, okay, is the last value greater than our last value? In this case, it's greater than our target, meaning the value, if it exists, it has to be in the row we're in. So we don't have to check the rest. And then I guess we could do like a binary search within that row. how you solve it. Okay. Let me share my screen. I think, what is it called? Search. 3D matrix. So I think there's an M for the rows and an N for the columns. How do they do it? So matrix.length, is that rows or columns? I'm gonna guess rows. You can check. Let's have chat write this as a test. I would use Claude, but they want you to log in. I do not want to log in. Oh. Yeah, this is what I wanted. I just want to check so is M3 and M is 4, right? I think that's right. think that's right. So we want to start at the middle 5th row. It's not length, huh? It's dot size. Might be. I don't know actually. I think length is like Python or something. But I think that's what he's using, so. Okay, and then we want to check what else do we want to check actually? It's 2 conditions. It's also, I think it's a while loop. How did we do the binary search? Okay, it was a left and a right. I'm gonna take this. Does the answer exist all the time? Okay. we only want to do the search if the target exists within that row. I think that's the idea. Yeah, we'll just say what am I missing? What? I think I'm doing this wrong. So we want the last value of mid Okay, if this is true, then we search. We search that row. Takes in a vector and a target. So what do we pass? I don't know how to pass the matrix. How do you pass the vector that we're looking at into search? We're gonna look that up. Also, does this question want us to do the... Want us to implement binary search again? I want to log in. Okay, I have an idea. Okay, we'll come back to this. Okay, the trivial way would be to just do a for loop. So we could say well, I is less than matrix dot size. So that would go through the rows. And we'll do another one starting at 0. And that would go through the columns. And then we could just check if matrix in the current row and in the current column equal to target return true. return false otherwise. I mean, yeah, that's kind of like the obvious lowest possible way to do it, right? Just iterate through the whole, iterate through every element in every row. Not really what I'm interested in though. Also it's not binary search. Yeah, I know I'm not passing anything. I zoom this in. Okay, what was I doing wrong? Okay, I was not checking if it was empty. Get the mid row. Isn't that what I did? Okay, I did do this. Get the last column index. Let's see. Last element, dot size. Okay, I did it wrong. It's dot size and then -1. Why -1? Last column. Okay. Yeah. Wait, mid row. Same thing. Mid row. I just called it mid. This means to keep searching in other rows, you need logic here. Right. This only catches the case in which the target possibly exists in the middle row. But if it doesn't, we have to binary search our way through the rest of the matrix. Meaning mid row would change. I don't like this. Let's see, how would it change? Okay, it would be like else. It has to be in a while loop, huh? I think I have to do whatever I was doing here. Okay, wait, I'm gonna delete this. See what he has.
Hey everyone, welcome back.
Let's write some more Neetcode today. So today let's solve, do you know an algorithm that can search for a target value in a sorted array? I know of one called binary search, right? And how efficient is binary search? Well, let's say the size of this array is n. We could do a binary search in log n time, right? But of course, we know that we actually have m different rows, right? So let's say we ran a binary search on every single row until we found the input target value, right? What would the time complexity be? Well, log n multiplied by m is going to give us a solution like that. So that's using the first property, knowing that each row's integers are sorted. And this is a pretty good solution, but can we do even better than this? I'll give you a hint. We're definitely going to have to use this second property that they told us. Each row itself is actually in sorted order, as in we know that the values in this row are going to be smaller than all of the values in this row, and all of the values in this row are going to be smaller than all of the values in this row. So can we use that property to, instead of searching through every one of these m rows, maybe we can actually do a binary search just to figure out which one of these rows to search in the first place. Because, for example, if we're looking for a target value 3, let's take a look at this row. This row could have any values between 10, which is the lower bound, and between 20. So obviously the target value 3 is not going to fall within that range between 10 and 20, right? So then the question is, okay, if the target value is definitely not in this row, we can cross this row out. But then which direction are we going to go? Are we going to look at the row above it, or are we going to look at the row below it? Of course we would want to look at the one above, right? Because above, the top row is going to have smaller values than the bottom row, right? So when we cross this row out, we can also say that, let's cross this row out too, because of course this row is going to have greater values. Dang good. To our cell, we can also say that, let's cross this this row out too, because plus here log n, right? Log n for binary searching the row itself. So that's a better time complexity than we had previously, right? Log m. Okay, 5, is that 3? Nope, 3 is less than 5. So what we can do in our binary search is cross out these values, cross out our pointers. Now our right pointer is going to be over here. And let's say we ran binary search again. We compute the mid to be over here. We check, is this 3? Nope, 3 is greater than this. So we cross this out and we shift our left pointer over here. Left and right are both here. Middle is going to be here as well. We're going to see, okay, either this has to be 3 or nothing, or 3 just doesn't exist. Of course, this is 3, so we found it. We can return true, and that's
Okay, that's what I was thinking. Okay, we did the brute force way. Can I see this? Oh, I have to pay for it. Okay. Yeah. Staircase search. Okay, so you start the search on the top right corner. If the current value is greater than the target, move left, value decreases. If it is smaller, move down. Binary search one pass, and then there's another one. That one. Neat. I think this is the one he did in the video. Okay, we compare the target with the row's first and last element. That's kind of what I wrote down in the whiteboard. That's how we know if we have to move up or down. So if the first value in our row is greater than our target, then we can move down a row, or be up a row. Then we do the same thing if the first value in our row is less than our target, then our target could live in that row, but we would have to check the end of the row to make sure. By checking the end, we would know that our target lives there because the last value in the row would have to be greater than our target. If the last value in the row was less than our target, then that means our target is greater than all of the values in that row. So we can move up. I think that's the gist. So, okay. Then he says binary search helps us quickly narrow down to that one row, right? Then search inside that row. So you perform a binary search within that row. Oh, this looks horrible to code. Okay, let's look at it because I don't quite understand it. So you have rows. So this is M, right? Rows and columns. Top and bottom. Rows minus 1. Okay, I don't quite understand this part. Is it because we're doing like a binary search? We're doing a binary search for the right row to search. Okay, that makes sense. So while the top. Okay, what is this? If target is greater than in the current row. Row is mid. Columns minus 1. So we're looking at the end of the row. If this is true, then we can move the top to the current row plus 1 for the row right after the one we're at. If this is false, then we have to check the first element in our row to make sure that the target is greater than. Yeah, so if the target was greater than, that means that the target exists in the row. And then we could do a binary search. It's horrible to look at. What is this one pass one? What is this? It says we can run one binary search from index 0 to rows times columns minus 1 for any mid index M. We can map it back to the matrix. Okay, let's do a different one. I don't think I'm getting binary search down. What's this? Okay, I'll jot down that I did. My solution was brute force. We should also just implement this one. Okay, let's try a different question. Okay, each index is a pile, and the element value at that index is the number of bananas in the pile. You're also given an integer, represents the number of hours you have to eat all the bananas. You may decide the bananas per hour rate. Okay. Oh God, what was that? Okay, I'm gonna take a quick break. Okay, let's see. Bananas per hour. Each hour you may choose a pile of bananas. Return the minimum integer k such that you can eat all the bananas within h. Huh? Let's see. We have 9 hours to eat what? Two what piles? Explanation with an eating rate of 2. How do you calculate the eating rate? Okay, it says, with an eating rate of 2, you can eat the bananas in 6 hours. With an eating rate of 1, you would need 10 hours to eat the banana, which exceeds 9. Thus, the minimum eating rate is 2. Why are we binary searching this? I'm confused. See the next example? It's Coco. Coco the monkey? What is the eating rate? Don't forget the question. Two bananas per hour. Yeah, I don't get it.
Hey everyone, welcome back, and let's write.
Solve Coco eating bananas. But before we do, I just want to say that if you do have any requested problems, you can feel free to leave those in the comments. I do have a large backlog of requested problems that I'm working through, so it may take some time for me to get there, but you can feel free to request variable. That's what we're trying to determine as the solution for this problem. Each hour, she can only choose one pile of bananas and eat K bananas from that pile. So that's what we're trying to determine, that K value. If the pile has less than K bananas, she'll eat all of the bananas, but she's not going to eat any extra bananas from a different pile. So what we're saying here is Coco can only eat at most one entire pile of bananas in a given hour. So what does that tell us? Already we're given some key information. Let's say we're given a certain number of piles, right? So basically the length of P, H must be greater than or equal to the length of P. Why is that? Because let's say we have 5 piles, right? So let's say we had 5 piles, and let's say this is what the piles look like. The values aren't too important, right? 1, 1, 2, 2, 3. And let's say we had H equals 4 hours. Well, let's say K equals some really big number, like 3, right? Basically the max of this input array. Okay, Coco ate this entire pile, Coco ate this entire pile, this entire pile, and this entire pile, because she could only eat 4 piles because we only have 4 hours, right? Coco can only eat 1 pile per hour. So if she ate all 4 piles over here, we'd still have 1 left over. That's why they guarantee us that H is always going to be greater than or equal to the number of piles. So the minimum in this problem, given this input array, H, the minimum it could possibly be is going to be 5. And I sort of wrote over it, but the last important thing that they tell us in the problem is we want to determine that eating speed K that Coco is going to eat at, but we want to know the minimum integer K, the minimum eating speed of Coco that she could eat all of the piles in exactly 5 hours, or exactly whatever that time interval, that number of hours happens to be. So let's take a look at this example. They give us an input array of 4 piles, and they give us 8 hours to eat all 4 of those piles. What's the minimum K, the minimum eating speed that Coco could use to eat all of these piles in at most 8 hours? So we have to eat all the piles in 8 hours or less. Well, the brute force would be to start at 1, right? Because Coco could try k equals 1, right? Can we eat all piles in 8 hours then? Well, it will take us 3 hours to eat the first pile, right? 3 divided by 1, which is our k, right? 3 divided by 1 is going to be 3 hours to eat this first pile. And to eat the second pile is going to be even more. That's going to be 6 hours, right? 6 divided by 1, 6 hours. So far we already have 9 hours, and we haven't even eaten the entire number of piles. So therefore, k equals 1 is not going to work. And we could just continue this brute force approach, right? Now try k equals 2, right? And then do the exact same computation with k equals 2. Now, my question to you is, we know that the minimum possible solution would be k equals 1, right? K can't be 0 because that would mean we're not eating any piles. So the minimum is 1. What's the maximum that k could possibly be given this input array and given this number of hours? Well, remember, the number of hours is always going to be greater than or equal to the number of piles. So in the worst case, k would basically be the max number that happens to be in our piles. For example, if k equals 11,
Okay, I'm gonna throw in the towel. I don't get it. It's such a monkey question. I don't understand it. What do people say about this? Coco should stop eating bananas. I agree. Coco eating brain. Understanding the problem was harder than solving this. Oh my god. Yeah, my brain is fried. To touch grass after this? I don't like Coco. I don't want to hear about Coco ever again. Question explanation. Coco has multiple piles of bananas. Minimum eating speed. Are we getting 6? This is 1, 2, 4. And a half. I'll come back to this one. Coco eating bananas. I'm gonna save it. I think I'll leave it there though.